She draws stuff. I don't draw anything, but my professor dragged us into a dance studio and started making us do weird things.
So she's having the more fun class.
I lied about that.
Yeah,
Well,
Good question. You said to take care of these. Did you want them the answers turned in? Or?
Mm-hmm.
Okay.
pretty much anytime we do this in class.
Right here.
Oh, wait, 1 second. I took it.
All right, 1 o'clock, let's get started. My video's going here. So, a couple of quick things. I'm having trouble with my microphone. I don't know, the last video, you can hear my voice, but then you can also hear like in the background. So I've gone to a different microphone. This is my old microphone. It's like duct taped. I think it's gonna be better. We'll see. All right. Next thing is if you have the mini exam that asked for you to email to me, last class I asked you to bring it hard copy. So if you've not turned it in hard copy, then you have a 0 for it. So I need the hard copy here. And then I also asked you for bonus to finish the 2 problems when we were finding the parametric surface vector functions. So if you have those, turn those in. Yes, okay.
Just turning in those 2 pages that have E and F.
Just as long as you have 2 answers, you can, well, yeah, you can do that. Just make sure your name's on it. And then the mini exams, is that the vector functions? Okay. The mini exams that you turned in last time, some of you just turned in, I'm going to pass those around. Those have been graded and put into Canvas. Some of you have made a lot of progress in terms of like what you submit to me in terms of a mini exam. You've worked on your penmanship, your clarity, in terms of neatness, keeping things in order. So I'm glad that some of you have. Some of you need to still work on it because remember it's about communicating your ideas with somebody else. Having a bunch of things scratched out and I can't read it, it's too small, that doesn't help your cause, all right? So I'm being less kind with the grading on that. Well, this is our last one pretty much, except for mini exam 8, which I just sent out in an email today, and I'm sure when you read it, you're like, what the hell? So what I'm gonna have you do is I sent out in an email, what is it, 16 pages? I don't know how many pages this review is for the 31 problems, 31 pages, whatever. It's a bunch of problems, right? So what I'm going to allow you to do is sign up for mini exam 8. Remember, you don't have to do this. If you've done 6 exams and you're happy with your grades, you don't have to do this. I'm only grading 6 of the 8, all right? So, yep. So if you'd like to get a grade for mini exam 8, what you're going to do is pick one problem off of here. I have the review up here, so you'll come up and you'll sign it next to the problem. You'll put your name, okay? And then you are now locked into that problem. No one else can do it. And what you'll do is you'll make a video, all right? Some of you don't have whiteboards. Most of you don't have whiteboards at home, but you go on campus, ask the tutoring lab to use a board. You're going to make a video, right? It's 2023. Everybody's making videos these days, right? So you're going to make a video, and it's going to be you working out the problem, right? Now, you can have the entire problem worked out already on the board, and then you can walk through it and talk through it, all right? Or you can do it if you have a tablet, you can do it on your tablet, you can have it worked out, and you can voice over it, just recording your screen. Or you can just use your phone, do a video like of the papers in front of you, all right? Any questions on that? Yes? Well, I haven't gotten to that yet. Let me get to it. Hold on. So that's what you need to do for the mini exam 8 grade, right? You have to request what problem. Does anyone know what problem? I think someone sent me an email already. Someone have problems? So I know you sent me an email. Did you send me an email yet? You sent it on Canvas. Both of you did. So.
When do we have to pick our problem?
Well, whenever you want before the deadline, but it might get picked before. So if you know the problem, then I'm going to hand it to you right now. You can find it on there and put your name next to it. Make sure I can read your name. And then, so you request that, okay? You can email me if you want, and I'll let you know whether or not the problem's taken. All right, first come, first serve on that. Now, in terms of submitting the video to me, I've sent you a link, right? I've sent you a link already to upload that video. It needs to be under 1 gig, all right? Under 1 gig. And it needs to be 1 video, not 10 spliced videos, right? 1 video. And the other option is maybe you have a YouTube channel or a server where you can store videos. You can just send me a link to it as long as it's not like virus, something like that. Hold on a second, let me get through this. And then the deadline is Sunday, May 7th, so that's not this Sunday, the following Sunday. I might share your video with the class if I think it's really good and it's a hard problem and it's something that maybe they would benefit from. I might send it, I might share it with the class, so just be aware of that. So if you don't want it shared, then when you send it to me somehow, just say, hey, I just want this to be for you, all right? And I won't share it. All right, what am I looking for? What am I grading? I don't want this shaky video where I can't see anything, right? I want you to actually make this a decent looking video. Hold on. Clear, clean video. Correct notation, no scribbles, no, oh, I forgot to put the symbol there. Y'all get what I'm doing, right? None of that needs to be precise. Legible, people need to be able to read it, and your explanation needs to be concise as well. Okay, question?
Oh, I was going to ask for sending the link. Would that be? Could we do that? Could we do that if it ended up being larger than a gig?
Yeah, sure.
Okay.
Yeah. What was your question?
So like I sent you 3 questions. Do you want me to write all 3 down, or just 1 for now?
1 for now.
Okay.
1 for now. The other two, you know what, do this. On the other 2 that you're thinking of doing, just put those, put next to it like the optional. Okay. Just put optional. Because you can do those even if someone else is not.
That's what I was asking.
So in addition to this mini exam 8, I'm also offering you an opportunity to do a separate video of you doing 2 more problems, 2 different problems, same thing. And that will replace your lowest mini exam score, or if you only have like 5 grades, then this will count as your 6th. Make sense? All right, same restrictions except for 2 gigs instead of 1. I don't think anyone's gonna have a 2 gig video. Is anyone shooting in like 8K? I doubt it, right? Right, it's probably not gonna be like 40 minutes long. I'm hoping these videos will be like 3 minutes long. Yeah, yeah. All right, enjoy. So what I want this to be is an opportunity for you to communicate the ideas with somebody else, right? And so the mini exams, that's one way of doing it, but that's just, marks on a page. It's different when you actually explain it to someone. Usually, if you can explain it, that means you understand it. So, all right, good, we're moving on. All right, the next order of business, I handed out a couple of pages here in color. Yes, thank you, thank you. All right, I had to hit the color copier today before anyone got to work so no one would ask me why I'm using color. All right, so this is going to be a nice little compact review of all of the different formulas that we're going to need for 13.7, which we're going to start today. And you are allowed to use this on the final, all right? I also don't mind if you mark up anything on here, add some stuff to it. Just don't, you obviously can't work out a problem on here and then say that, then take that to the final, all right? So any additional notes you want to put, that's fine, okay? All right, let's get down to business. My goal is to finish the book, right? Chapter 13, section 9. We are in 13.6. We have today, we have 2 days next week. I want to finish the book. So I ask today that if you have questions, that unless they're like a dire question about your basic understanding of what's going on, let's just move this train forward, all right? Got it, everyone? Yes? Okay. Now, if you're confused, you need clarification, I want you to ask, but let's stay off abstractions today. All right, so last class we ended, and I actually used this formula to prove that the surface area of a sphere of radius 1 is 4 pi. right? That's what we ended class with. So we're talking about this integral that gives us surface area, right? I just passed it up. There it is, right there. So if we can draw a surface S with the parametric functions or vector functions, or a vector function, r of u v, if we can draw it, then we should be able to calculate the surface area by doing that integral, which is the magnitude of the cross product of the partial derivatives of the vector function, right? Okay. So we are going to continue now. We are going to skip this note, all right? And we are going to, we're going to skip that one. We're going to find the surface area, okay, the surface area for the part of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. Okay, so we have this paraboloid, z equals a function of x and y, so that's a surface. That's a good old-fashioned surface from earlier in this class. And what we're trying to do is find the surface area of that surface, but we are restricting it so that it's between these two cylinders. Now notice these cylinders, x squared plus y squared is 1, is a cylinder that opens up through the z-axis, has a radius of 1. And then x squared plus y squared equals 9 is another cylinder that opens up through the z-axis that has a radius of 3. So we're trying to find the surface area of that surface that's floating with these two cylinders punching through it, which creates almost like a disc shape, but it's wavy. Let me just show you the picture. Let me bring in, we have the orangish thing is the surface that we started with, right? The paraboloid. And then we have the two cylinders, the red one and the green one, that punch up through this thing. And so we're trying to find the surface area of that surface right there. Do you all understand from the illustration here what we're doing? Yeah? Okay, so we need to first see if there's any way that we can draw this thing, right? Like that's what we spent all that time, that handout, we spent all that time the other day, last class, trying to draw a surface, right? So let me see, how could we draw this? Well, remember, this comes from, get this out of here. I'm going to make this a little smaller here in the corner. Maybe not. Okay, this is coming from this surface, z equals y squared minus x squared, right? So looking at this, how in the world do we do that, right? I mean, this is a little more complicated than the ones that I gave you, right? A little bit more complicated. You can look at it from the top. If you look at it from the top like that, that should be pretty easy to draw. It's like a disc, right? It's like a disc that the center's been taken out. And that would be in the, what planes is it, or what plane is this in? It would be the xy. So can we draw a disc in xy? How do we do that? Let's see. R of uv. So draw me a disc in xy. That would be, we need cosine, right? Cosine and sine for the x and y respectively, but we need to be able to adjust the radius. So I'm going to put v cosine u, v sine u. I'll worry about the z in a second. The v here and the u have restrictions, right? My restriction on u is going to be 0 to 2 pi, because that'll draw me the whole disk, right? 0 to 2 pi. And what's the restriction on v? Well, we've got to go from the inner radius to the outer radius, right? So from 1 to 3. You all following? That should draw me a disk that has a hole in it. But I need that disk to have a z value that fluctuates, right? And that z value must follow that right there, shouldn't it? It needs to follow this surface. This is the equation of that surface. So can't I just plug that value in right here, y squared minus x squared right here, but replace the x and the y with the two component functions I have here, right? So this last component should be y squared. So y squared for us would be v squared sine squared u. That's y squared. And then minus the x squared. What's x squared? V squared. I'm out of room. Cosine squared u, right? Questions? Yes?
If we factor out a negative b squared, oh, never mind.
Yeah, almost. If it was a plus, that'd be great, wouldn't it? It's not a plus, unfortunately. Yeah, I was thinking the same thing. Man, if that was a plus, we could factor out, and then we got Pythagorean. But that should draw it. There's another identity, cosine, double angle, but let's just stick with this. All right, do we have any questions on why this draws that surface? Okay, now I need to find surface areas, so I need to take partials, and I need to do cross products, and I take magnitude, right? Messy, right? This is going to be messy. So let's take the partial derivative of r with respect to u. That's going to give me a vector. I'm going to get negative v sine u here. Here I get v cosine u. And then with respect to u here, boy, that's going to be a mess, isn't it? Isn't this going to be a mess? Yeah? We're going with respect to u, so v squared is going to come for the ride. I'm going to take derivative of sine squared. So the 2 comes out. I'm going to bring the v squared there. Derivative of sine squared. The 2 came out. Then I have to take derivative of sine, which is cosine u. Oh, man, this sucks, doesn't it? And then over here, we do the same thing. I have minus, let's see, the 2 comes out. I've got the v squared, but then the derivative of cosine is, sorry, I need the cosine here. Cosine u. I need derivative cosine, which is negative sine. Well, that's going to change that to a positive sine u, like that. Ugh. Okay. Do y'all see how bad this is? I mean, it's not the end of the world, but I mean, it's not nice, is it? Yeah. So, there is a shortcut, all right? I wanted to start with this just to show you just how bad this is starting to get. And I skipped over a note, right? I want to go back to that note now so that you can appreciate what this new note is telling us, all right? So I'm going to say right here, like, we are not happy about this at all, right? This is trouble for us. So let's scroll up. It says here that we can look at this formula for surface area a little bit different if we have that our surface is z is a function of x and y, which is exactly what we have here. The surface we're looking at is a function of x and y, right? That's it right there. You can say that this is a function of 2 things. If we have that, then the surface area just becomes this integral. Now, I'd like to show you why, because I mean, it's important. If we're going to use it, I do want to show you why that integral becomes this instead. So let me try and develop this for you. Where do I want to do this? I guess I'll do it right here. I'm going to leave that up there, just like that. Okay. So you know how when we were making all those formulas last class, R of UV, right? And we were trying to come up with these 3 components, right? That would draw our surface. What this note says is that if you let the U just be X and you let the V be Y, then how could I draw that surface over there? So instead of using u and v, we're going to have a vector function that's going to have x and y in it instead. The x coordinate's just going to be the x coordinate. The y coordinate, or the y component, is going to be the y. And the z is going to be whatever this function is here. So we're looking at this as some function of x and y. I'll call it f. This will be whatever that function is. So the x component is controlled by x. That's like the domain on the ground. The y component's controlled by the y. on the ground, so your domain's down on the xy plane. And then your surface, your z, is living up above it, right? See, this is very different than what we did before. Before, the u and the v were like clocks running in the background, and we couldn't see the clock. We just know that u and v are changing. Here what we're doing is we're saying, you know what? We're actually going to try and visualize the u and v as being physically part of the xy plane, right? So we can actually see the domain on the ground. The only reason we can do this is because this relies on two variables, x and y alone. And these two don't depend on anything else. This doesn't depend on z or y. This doesn't depend on x or z. So if we do that, okay, if we do that, then what would the partial of this be? So normally we do the partial with respect to u, right? But here it's partial with respect to x because the x is now the u. What would that be for us? What's partial of that with respect to x? 1, 0. And then that we don't know what it is, right? I'm going to notate it this way. F with the subscript x. Everyone understand that's the partial of f with respect to x? Right? And then what would the partial with respect to the other variable y be? 0, 1, partial of f with respect to y, right? And now I'm supposed to do the cross product of those. And when we do the cross product, we cover these up. What do we get first time through here? We get this minus that. So when we do this cross, we will get a vector. The first component of that vector is negative partial of f with respect to x, right? That's 0, take away that. Comma. Now we do the middle component. We get a negative. I'll put the negative in front. And then we get partial of f with respect to y minus nothing. So just minus partial of f with respect to y. And then the last piece will be 1 minus nothing. So just 1. And now that's the cross product, right? That's Rx crossed with Ry. Now for the formula for surface here, I need the magnitude, don't I? If you take the magnitude of this vector, it's the square root of that squared plus that squared. Well, yeah, the square root of that squared plus that squared plus that squared, which is that. You see? So that only works if z is a function of x and y. Similarly, you can do the same thing if, like, here we had z was a function of x and y, right? So that became that. You can do a similar argument if your x is some function of y and z, or if your y is some function of x in z. As long as one of your variables depends on the other two, and those two are free to be whatever they want, then you can do a similar argument and go through this same thing and get a formula for each one of these scenarios. All right? Now, I will allude more to that when I get to the handout that I gave you, but that's in the next section. All right, so with that tool in our hands now, I'm going to go back to this problem that we were not happy about. And we don't need the picture anymore, right? We have the surface we're looking at's right here, right? That is our function of x and y. It is y squared minus x squared. And I'm now going to use the formula. Because I have that scenario, I'm going to be doing the double integral over d square root of 1 plus, I'm going to use the notation I used just a second ago, partial of f with respect to x squared plus partial of f with respect to y squared dA. Right? That's the formula we just had right here, right there. Okay? All right, so let's set it up. This is the double integral over d. What's d? What's d? That's the domain, right? That's the shadow of that surface down onto the ground. Very important that you see that. We've got this, it's hard for me to draw that. That's that thing with the hole in it, okay? But then down on the ground, right? Down on the ground, on the xy plane, I have the domain, which is an actual like washer down there, right? It's flat. This is D, this is S. Don't confuse the two, right? This one's wavy, this one's not. So the surface area of S, right? The surface area of S is going to be the double integral over that domain of the square root of 1 plus the partial of f with respect to x, which is negative 2x squared, plus the partial of f with respect to y, which is 2y, that quantity squared, dA, which is the double integral over d of the square root of 1 plus 4x squared plus 4y squared dA. We are now back in the double integral section, all right? This is just a double integral back from before. We're trying to evaluate this function, right, over this domain. We look at that domain on the ground and we say, hey, is that type 1? Is that type 2? Is it polar? Polar, right? Isn't that a great polar region there on the ground? I'm going to draw that region D. I'm going to draw it like this. So looking at it from the top, it's like this. Right? This is 3. This is 1. That's your D right here. And so if I want to represent that in polar coordinates, I'm going to say, okay, I want my theta to go between 0 and 2 pi, and I want my radius to go between 1 and 3. And now I'm going to come over here and I'm going to convert this to polar. Every time I convert to polar, all the x's get replaced with r cosine theta, all the y's get replaced with r sine theta, right? And we get lucky here because you can factor a 4 out of both of those, and you'll get 4, and then in the parentheses you'll get x squared plus y squared, which is? Careful. We're in polar, so we're not fixing ourselves on the outer edge or inner edge. Just polar in general. What's x squared plus y squared in polar? R squared. R squared, right? So I'm just going to put it here. This becomes that right there, and then that is r squared. Because we're in polar now, right? Okay, so now here's our new integral. I can actually put limits of integration because I have my limits of integration here. 0 to 2 pi, 1 to 3, and then square root of 1 plus 4r squared, right? 4r squared, because I had the 4 that I pulled out, r squared. Drum roll. R, because we went to polar, is outside the integral. R dr d theta. And at that point, we're in business. I'm not going to go through that integral. It's a basic u sub, right? Basic u sub here. And right, let that be u. There's a derivative. You're off by a constant. Anyways, I worked this out. Oh, I worked it out on the computer. That's right. I had the computer get me the answer. I did it by hand, and I got the same answer. It comes out to be approximately 111.98. That would be the surface area of that surface. Okay? That is a much better approach than what we had started with. All right? And that's going to carry into the next section. If we look at a surface, if we can get it to be a function, like get one of the variables to be a function of the other two, then we want to use the shortcuts. We don't want to use that clunky, like crossing RU and R partial of R with U and partial of R with V, because that can get messy. All right. Was that?
56, question 6.
Yeah. What about it? That's what it says. Yeah. Yeah. So these are problems that you should look at, all right? These are problems from this section you should look at. Some of them are asking for tangent planes. That's what this section started with. And then the second half is asking for surface areas. And then number 56 is a bonus to be turned in the final. There's a cool one. These are the actual pictures that go with these. I think number 42 is a really cool one because it's, do you remember when we were doing vector functions way back earlier chapter and we drew that like spiral that goes up? This is basically that same picture, except it's like a ribbon instead. A ribbon that goes up, almost like an auger bit, you know? And so we can find the surface area of that. It's a pretty cool problem. All right, we are moving on.
What's the equation of that real fast, if you have
It's V cosine U, V sine U, V.
Okay, interesting.
So it basically draws you, if you look at it from the top, right?
Yes.
If you look at it from the top, it's just drawing you a disk. But as it draws the disk, right? Wait a minute, hold on. U, is it U or V? Hold on. You want it to grow, yeah, so, no, I think it's U. Because as your angle turns, you want to go up. And if you say V, then it's stuck between two numbers. Yeah, hold on a second. Yeah. Anyway, it's in the book. It's in the book. I forget what the restrictions are. All right, we're moving on. 13.7. We will be in this section for the next day and a half. All right? Oh, that's not where it starts. Let me go. I told you chapter 13 was pretty heavy, right? I wasn't kidding, was I? Okay. So I want you all to take a look at this new definition. A surface integral of f over s. So I have a double integral over some surface. Then I have a scalar function, f of x, y, z, ds. Here, this ds stands for this, which in the previous section was surface area, wasn't it? I mean, that's exact. If I take this out, well, if I put a 1 here, right, then that's just surface area, isn't it? So what we're doing is we're now taking the surface area and multiplying it by the function. So there's an analogy to this. We've done this already. When we did a line integral where we had f of x, y, z, d little s, not capital S, d little s, what we said is, okay, you've got a curve here. That curve C lives in three-dimensional space. And then what we're doing is at each point, we are plugging that point, the x, y, z, into some function. And so we're adding up the value of that function all along the curve, which if this is like a density function, or if this is a density function, that would give you the mass of this wire. Okay, so this basically takes the sum along all the points of that function. This takes the sum of all of the points along a surface instead of along a curve. So now what you have is a surface living in three-dimensional space, S, and you're going to every single point on that surface, and you're plugging every point into this scalar function. You're getting a value out, and you're adding all of those up. All right? So we've seen this. It's just we're in a higher dimension now, right? We're not on a curve anymore. We're on a surface. So what I'd like for us to do is our first example. So the only new thing here from the previous section is we have to deal with